Hello everyone, this is Dr. Vishal Trivedi from Department of Biosciences and Bioengineering, IIT Guwahati. And in what we have discussed so far, we have discussed about the extraction of the products from the cells which are overexpressing your protein. So, in the previous lecture, we have discussed about how to break these cells with the different methods. So, we have discussed about the physical methods, we have discussed about the chemical method, the enzymatic method, and as well as at the end of the previous lecture, we have discussed about the mechanical processes. So, all these processes are actually going to release the content which are being intracellular, and then the product or the protein which you are going to overexpress into these genetically modified organism is released, and now the next step is to purify these proteins from the complex mixtures. So, once the product is released from the cells which are overexpressing the protein, you have different types of proteins. So, most predominant protein could be the protein which you would like to purify, but the protein of other proteins such as the protein from the host will also be released in this process, and those proteins will going to be make the task very difficult, and in that process you have to ensure that you will get your desired protein, but at the same time you will going to remove the other proteins. So, your protein which you would like to purify is called as the desired protein. The protein which are being given from the host are called as the impurities or the contaminating proteins. So, in today's lecture we are going to discuss about how to purify or how to isolate the protein of your interest. So, this process is being extensively being done simply by employing the chromatography techniques, but before getting into the details of chromatography, we are going to discuss about the basic principle of separation. Let us assume that for explaining you the basic principle of separation, we have taken an example of 3 molecules, and we have taken a very simple molecule of the organic molecules. So, the molecule number 1 is known as the benzene, the molecule number 2 is the phenol, and molecule number 3 is the aniline. And imagine that you have a mixture of these 3 bioorganic molecules. First thing what you have to do is, if you would like to separate these molecules, you have to understand the characteristic of these molecules. Let us see what are the characteristics are present in these molecules. So, the molecular formula of benzene is C6H6, the molecular formula of phenol is C6H6O, and the molecular formula of aniline is C6H5NH2. The mass or the molecular weight of these 3 molecules are 78, 94 and 93. Similarly, the density of the benzene is 0.87 grams per centimeter cube, phenol 1.07 and the aniline is 1.02. The melting point is 5.5 degrees Celsius, whereas in the case of phenol it is 40.5 and for aniline it is the minus 6.3. And the boiling point is 80.1, 181.7 and 184.13. So, what you can see is all these 3 molecules are varying in terms of the many of the physical properties as well as the chemical properties, and this is actually the basis of how to separate the molecules. So, if you would like to separate the molecules, what you are supposed to do is you have to know their physical properties, chemical properties as well as the biological properties, as long as we are talking about the protein as well. So, we have taken an example of 3 molecules, that is benzene, phenol and aniline, and they look like very similar to each other, but they have the distinct physical and chemical properties which could be used as a criteria to separate them. The physical and the chemical properties which can be used to separate the molecules are molecular weight. So, if the proteins are if the molecules are of different molecular weight, you can employ or you can exploit that criteria to purify that. I would like to have a molecular weight, I would like to purify a molecule which is of molecular weight of 40, and that actually is going to exclude all the molecules which are above to that or lower to that. So, that kind of criteria also can be used. Similarly, you can use the boiling point. In case a boiling point can be used only if you would like to purify the two molecules which are liquid in nature. Similarly, we have the freezing point, crystallization, solubility. So, the crystallization is one of the criteria or the physical property which people were using very often to purify. So, what you can do is, suppose you have a complex mixture, what you can do is you can bring the conditions which is of the crystallization conditions of the one molecule. So, what will happen is, if you take the liquid which is actually a mixture of the different compounds, and then if you bring the crystallization condition of one of the compound, that one compound is going to be crystallized, and that crystallized product you can purify simply by filtration, and the rest molecule will get filtered out, and then you can wash this crystallized product, and you can recrystallize again, and that actually will give you the very high purity compounds. This is exactly what people do when they are producing some of the very high quality chemical compounds. One of the classical example is sugar itself. So, what people are doing is they are getting the sugarcane juice, and what they are simply doing is they are just bringing the crystallization conditions of the sugar, and that is how they are actually making the sugar from the sugarcane solution or sugarcane juice actually. Similarly, you can do a crystallization of the different organic compounds, because all the organic compounds are having the different crystallization conditions. So, if you vary those conditions, you could be able to crystallize your compound of your interest, and that is how you can actually get that compound from the mixture. Similarly, you can use the solubility. Solubility and crystallizations are very similar properties. The molecule which is going to crystallize in a particular condition is also going to have the different solubility. So, you can also use the solubility as a criteria. For example, if some molecule is more soluble in water, but less soluble in benzene, you can just simply dump that particular complex mixture into the water, and as a result what will happen is all other molecules are going to be not soluble. So, they will make the different layer, whereas your compound will get fractionated and it will go into the aqueous layer, and that is how you can actually be able to purify. If you remember, when we were doing the plasmid isolation, that time we were doing the phenol chloroform treatment, and in that phenol chloroform treatment you were getting the two layer, one is aqueous layer and another one was the phenol layer, and the DNA which is actually the polar molecules, it was migrating to the aqueous layer, whereas the protein and all other molecules, they were being going into the phenol layer, and that is how you are actually separating the DNA from the protein as well as the other contaminating molecules. So, that can be used as a criteria to purify the molecule as well. Then you can use the density, you can use density also. Then sometime when the physical properties are not good enough, people are also using the chemical properties. For example, the functional group, if you see all these three molecules, benzene does not contain any functional group, whereas the phenol contains a functional group of OH, and aniline contains the functional group of NH2. So, once you have the functional groups, actually you can exploit the functional groups because these functional groups could have a differential reactivity, and that differential reactivity could bring some kind of alteration in terms of its physical properties. For example, if you make a complex of some compound that actually will reduce its solubility, then what will happen is that particular compound is going to be precipitated if you add that reagent, and the other two molecules are going to be remain in the solution, and that is how you can be able to purify remaining compounds. And at the end we also can exploit the biological properties. So, the biological properties are mostly been associated with either the DNA or the protein, which are biological in nature, the molecules, and that we will discuss anyway in detail in the subsequent lectures. So, let us see a clear example how you can do a separation. For example, if you have a mixture of benzene and aniline. So, you have complete mixture of benzene and aniline and you are using the boiling point as a criteria. So, if you remember the benzene and aniline are having the different boiling point. So, what we have done is we have started putting it into a condensation reactions or condensation apparatus and we started heating up this liquid, and as soon as we start heating up the both the benzene as well as the aniline is going to form the vapor phase. So, the benzene is going to be fractionated into the two phases, one is called as the vapor phase, the other one is called as the liquid phase. So, the both molecules, the benzene as well as the aniline is going to distribute themselves into the two phases, one is called as the vapor phase and other one is called as the liquid phase. So, in the beginning the both molecule are going to distribute themselves into the two phases, but as the process will continue, because the benzene is going to have the different boiling point, the benzene will prefer to be more into the vapor phase, whereas the aniline is going to be prefer more into the aqueous phase. So, as a result what will happen is that the benzene will prefer to be into the vapor phase and it will come into the condenser, and then within the condenser it is going to be condensed and then you can collect the benzene into the separate flask, whereas the aniline, the mostly the aniline is going to be remain into the liquid phase as long as you are keeping the temperature up to the boiling point of benzene, and at that point when you are bringing it to the boiling point of benzene, the more and more amount of benzene is going to be collected into the other flask. So, if you continue this process, in the beginning there will be a mixture of benzene and aniline in the top flask as well, but if you continue this process, the amount of aniline is going to be reduced in the subsequent distillations, and at the end what you are going to have is the pure benzene into the top flask and the pure aniline into the lower flask. And this phenomena of distributing the molecule into the two phases is actually the basic principle of separation, and the parameter which actually measures the distribution of the two molecules or distribution of molecules into the different phases is called as the distribution coefficient. So, the formula for distribution coefficient is that the Kd is equivalent to the concentration of the molecule in phase A versus the molecule in of the concentration in phase B. So, in this particular case you are going to have 2 Kd molecule, 2 Kd values, one for benzene and the other one is for the aniline. So, aniline is going to have the separate Kd values and the benzene is going to be the separate Kd values, and because of that the Kd values for benzene would be more towards the vapor phase, whereas the Kd values for aniline would be more towards the liquid phase, and as a result the benzene will go and get distilled into separate flask, whereas the aniline will get into remain into the original flask. So, this is actually the basic principle of separation, but as long as the protein is concerned, you cannot use the boiling point or melting point and all any such criteria to separate the proteins, because the proteins are very delicate molecules, or they are gentle molecules, they are actually having a defined predefined three-dimensional structures. So, the protein has to be a protein or the molecules of biological in nature, which actually requires some kind of activity and three-dimensional structures and all those kind of parameters. Those molecule has to be purified in a more sophisticated techniques, and those technique is known as the chromatography. So, in a chromatography, the purpose of the chromatography is to separate a complex mixture into the individual component, exploiting the partition effects which distributes the molecule into the different phases. So, the basic principle of separation remains the same, except that the process or the way in which you distribute the molecule into the two phases are different as in chromatography compared to the boiling point or melting point and all other kind of those harsh processes. The distribution of a molecule between the two phases A and B is given by a distribution coefficient Kd. If you remember in a previous slide, the Kd is the concentration of the molecule in phase A divided by concentration of the molecule in phase B. But in compared to that, in most of the chromatography technique, the phase A is considered to be a stationary phase or the matrix, whereas the phase B is the mobile phase or the buffer which you use for the purification. Now, let us understand how the distribution or the separation techniques works in the case of chromatography techniques or chromatography procedures. So, in most of the chromatography procedures or the column chromatography procedures, you are actually filling a column with a bead or some matrix. So, matrix are nothing but the beads. For example, these beads could be of silica beads, or it could be of agarose beads, or it could be some cellulose beads. So, you can imagine that some circular beads like are being filled, and that actually is making a column of a chromatography technique. Now, these beads are actually being arranged in this fashion, and as a result the beads are actually making a layer after the layer. So, these beads are sitting onto each other, and as a result they are actually making a multiple layers. And what happen is that once the molecule X or Y is interacting with these beads, they are actually experiencing the distribution. So, as soon as the X or the Y or Z or A, B, C, any molecule, when it is interacting with these beads, because the beads are not alone, they are also having the water. So, the X, which is actually, as soon as X will interact with the first layer of beads, it is actually going to distribute themselves between the aqueous phase and the bead phase. But so, depending on their distribution, they will distribute themselves towards the bead phase versus the aqueous phase, and that actually will continue from the first layer. So, you can imagine that the beads are having the first layer, then this is the second layer, third layer, fourth layer. So, you have one layer, second layer, third layer, fourth layer, like that. And when you flow the water from the top, the molecule which are present into the layer number 1 are again going to distribute with the beads which are present on the layer number 2. That is why, and that will continue until the distribution will going to make the separation between the two molecules, and that actually is going to make wider separation between the two molecules, because the molecules are going to experience not only one distribution or one Kd values, they are going to experience multiple Kd values depending on how many layers of these beads are being packed in that particular column. And as a result, that is why if you have hundreds of molecules, these hundreds of molecules are going to experience hundreds of Kd values or hundreds of distributions, and as a result you will see that a molecule A is being separated from the molecule B. Let us see how this is being done in the real values or real way. Now, imagine that you have a column, okay, where you have filled the stationary phase is filled into a cylindrical tube made up of glass or steel. The matrix of mixture of analyte is loaded onto the top and it runs from top to bottom. Now, let us see how the Kd is exploited in a column chromatography. Assume two molecules X and Y with a Kd value of 1 and 9 is being loaded onto this. So, you have two molecules which are having a Kd value of 1 and 9 against this particular column. Okay. Now, if they are traveling through this column, so what is mean by 1 and 9 is that if they are traveling in this column, and suppose you make the different layers of these beads, and I assume that every bead or every bead volume is 1 ml actually. So, what will happen is that suppose you loaded 5 mg of the X and 5 mg of Y, okay, and you can see that X is having a lower Kd values, whereas the Y is having the higher Kd values, which means that the X is preferring to be remain with the aqueous phase, whereas Y is preferring or Y is distributing themselves to the matrix phase. So, as soon as they will interact with the first layer of matrix and you have flown 1 ml of buffer, what will happen is that they will distribute this 5 milligrams which is of X and Y according to their distribution plane, according to the distribution coefficient. So, what will happen is that X, what is the distribution? 1, right. So, X is going to distribute between 50-50. 1 is means the Kd value of 1 means that the concentration of material in the matrix versus the concentration of material into the aqueous phase is going to be equal at any distributions. This means in the first layer you are going to have 2.5 mg of X, and the 2.5 mg of X will go into the aqueous phase. Similarly, for Y it is actually be distributed in terms of 4.5 versus 0.5 because the Kd value is 9. This means the Y, the 4.5 milligrams of Y will be bound to the first layer of your beads or the first layer of the beads, whereas the 2.5 milligrams of X is going to bind to that particular bead. Now, if you flow 1 more ml, what will happen is that the 1.25 milligrams of X is going to be transferred to the layer number 2, that is for the from the X, and the 1.25 from the aqueous is going to be transferred into the first layer. So, because of that, if you see that the X is actually preferentially going towards the aqueous phase, which means more and more X is going into the aqueous phase, and you know that aqueous phase is running faster than the matrix because matrix is stationary. So, the Y will remain there, and if you start in the beginning, the X and Y will remain onto the top, but once you run this column for longer period of time, the Y will go and bind to the beads, and that is how they will be going to be remain on top of the column, whereas the X proteins or X molecules are going to travel faster with the aqueous phase, and that is how the first your X will come out and the subsequently the Y will come out, and that is why the Kd values are actually distributing the molecule between the two phases, and that is how they are actually controlling the overall separation. Now, if you see how and monitor this particular type of elution of these molecules from the column, you will get a pattern which is called as the chromatogram. So, what is the chromatogram? The plot of elution volume along with the absorbance, or you can use any parameter, is known as the chromatogram, which is given in this particular figure. The volume or time it takes for an analyte to come out from the column is known as the retention volume or the retention time. The chromatogram may have separate peaks. For example, in this case the peak A and peak B are the two separate peaks which are not having the overlapping base, whereas you can have the peaks which are having the overlapping base, which is actually the C and D. So, what you see is the C is actually, if the D is not present, the C is eluting in this way, whereas the D is eluting in this way. That is why, since they are actually sharing the base, that is why these two peaks are not being separated. So, the column is been able to separate A and B, whereas the column could not be able to separate C and D. So, what actually determine or what actually can be used as a criteria to see whether my column is good or bad? So, the ability of a column to separate the two molecule is known as the resolution, and the resolution is depending on two parameter. One is called as the distances between the two peaks, which means the peak between A and B, and so it is actually dependent on the delta t, which means actually the distances between the two peak, whereas the resolution is also dependent on the average width of the two peaks which are neighboring peaks. So, the ability of what is resolution? The ability of a chromatographic column to analyze or separate two analyte peak from another is known as the resolution. It is defined as the ratio of differences in the retention time between the two peak and average of the base of the peak, which means the resolution is directly proportional to delta TR versus WAV. If you have a resolution value of 1, you could be able to see 97% separation of two peaks, but if you have a resolution value or resolution value of 1.5, that is considered good, because that is going to give you the two separate peaks, or that will give you the separation of more than 99%. The number of distribution. So, what actually is governing the resolution? The resolution is being governed completely by the number of distribution planes, because if you have the number of distributions, it is going to having the higher chances of separating the two molecules into the two separate peaks. That is why the number of distribution events govern the ability of a column to separate the two analytes. In other words, the resolution is directly proportional to the number of distribution event. In column chromatography, each thin plane of column matrix participate in distribution of a molecule. Now, you can assume that the if you have a bead and its diameter is d, this means the individual planes which are going to make the distribution is actually of the d height. So, if you have a column of h height, you can actually be able to calculate the theoretically how many number of distribution planes are present. So, you can imagine that if the height of a distribution plane is h, which means the diameter of these beads, and the length of a column is L, the number of distribution plane in a column is given by the n equal to L by h, and if you solve this, you can get the n equal to 16 TR by W whole square, or n is equal to 5.54 TR by W half whole square, which means that n is going to control the resolution. And how you could be able to, how the n is controlling the resolution? The n is controlling the resolution in two ways. It is controlling the two parameter. As the number of distribution plane will go up, it will allow the analyte to travel for longer period of time. Consequently, it will going to increase the distances between the two peak, which means it is actually going to increase the delta t between the two peaks. If you increase the delta t between the two peak, you are actually going to increase the resolution, because resolution is directly proportional to the delta t. Now, as the number of distribution plane will go up, it will going to reduce the width of the base of a peak. As a result, the peak will become more sharp, which means it is actually going lower down the W of a peak, which means it is going to make the peak width lower, which means eventually it is going to lower down the PWAV between the two peaks, which means it is going to increase the resolution, because if you reduce this, you are going to increase this, because the resolution is inversely proportional to the 1 by AW. Now, you can see how the number of distribution plane is affecting the peak width. Okay. So, now you can see in this figure, when you have the number of distribution plane to 10, you are not going to get a peak. In fact, you are going to get a flat peak or flat plateau actually. If you increase the number to n equal to 100, you are going to see a peak which is very having the very big base. but if you increase the n to the 1000, you will see a decent peak with a narrow base, which means if you increase the n, you are actually going to reduce the base of the width, and as a result the peaks are going to be sharper and sharper. As the number is increasing, the peak width is decreasing, hence the number of distribution in an indirect way to measure the column efficiency, higher the number is desirable for the better separation. So, this is all about the separation of the two molecules under the column chromatography. So, with this we would like to conclude our lecture here. Thank you.